the young researchers in this field are forging ahead, unabashed by the health situation, and that the Zoom meetings are trying to, replace to the extent possible the live contacts between the generations. So let me just start by sharing my screen with you. Can you see? Ah, okay. So the announced title was How I Got to Love Dynamical Systems and Their Bifurcations. Actually, the abstract will not convey precisely what I'm going to say, but that's usually the case. As Valerio already mentioned, this is with 1,000 thanks to the great companions, many younger and some older, on this exciting road. And if you're interested, probably the best place to look at is the website at UCLA still, or on ResearchGate. So I will start by asking, what is climate? Which is really the question that in some sense got me into trouble. I would suggest to subsequent speakers who I think have maybe somewhat different opinions on this to also start with such a slide, or at least have such a slide somewhere, or some form of definition. So what is climate? Well, some sort of average weather. Okay, but what sort? The first thing that comes to mind is average over time. Traditionally, 30 years represent the climatological mean, but then why not 40 or 50? As a matter of fact, I have an anecdote about this, about the famous meteorologist Gotske, who had studied physics and shortly after the war was looking for a job, and he was interviewing at a Danish Met service. So he very honestly said, I haven't studied meteorology. What do you need to be a climatologist? And the answer was, add 30 numbers and divide by 30. So this is clearly not where we are today. Then you could think about averaging over infinite time, which is well-defined and self-consistent, but then climate cannot change. Of course, we all know that it does. So then, you might think of an ensemble average, but what ensemble? So, for instance, the planet of the solar system, there are 8 of them, used to be 9, but one was demoted, Pluto. So the terrestrial planets don't look at all like the Jovian ones, and among the terrestrial ones, Mars doesn't look like Earth or Venus. So this is where I fell into the hole, into the rabbit hole, as this famous mathematician who wrote about the little Alice said. So how about the invariant measure mu of the attractor A of a dynamical system, like this? And interestingly, some of you might know that we had a little trimester on math and climate at the Institut Henri Poincaré in Paris last fall. So one of the invited lecturers, Martin Clausen from Hamburg, when we had during the first week of the trimester discussion of what climate was, wrote this definition, which I love because it also shows, the spirit of interest in the humanities, Humanioren, as it is called in German, following Aristotle's definitio fit per genum proximum et differentiam specificam. In other words, you have to say what the class is within which you fall and how you differ from the other members of the class. We can describe the climate system as a dynamical system consisting of thermodynamically open subsystems being externally forced, well, he wrote driven, but it fits more better into the language here, dissipative and high dimension. So again, for those people who think that dynamical systems only deal with low order systems, they should go to a few books by, Foyash, Temam, and other people. So the consequences of this definition are interesting. We have to treat the system as stochastic, and thereby we run into the ergodicity problem and the attributional detection issues. So the definition above, in other words, this item with this equation worked fine from about 1960 till about 2010, using forcing that is fixed in time. So that's 50 years, not bad. But now we have to seriously worry about anthropogenic climate change, so we'll adjust equation 1 a bit to accommodate time-dependent forcing. So we wind up with a stochastic differential equation, or it can be a stochastic partial differential equation. At any case, let's keep it simple, okay? In which, aside from the deterministic term, which is typically nonlinear, you have a stochastic term with the noise, if it's not a function of x, being called additive, but it is a function of x and it is multiplicative. And so this mu becomes a mu that changes in time, and a also changes in time and is a function of realization in some probability space that I come back. So the usual definitions of a time-dependent measure, a random attractor, and the Wiener process, both of which will be discussed later in the talk. So since I hinted at personal history, you know, again, I got a BSc and an MSc at the Technion, which lasted a little bit longer than usual because of concomitant service in the military. But as it happens, it is the first time that I met one of the great figures of the previous generations, Sidney Goldstein, who had just retired from Harvard and who's a person who really wrote modern developments in fluid mechanics. And well, it wasn't with him that I really did my research work, but I was his teaching assistant. And my first two papers were on heat transfer across a common vortex tree. And this is also where I first read about Raymond Hyde's work on the rotating differential heated atoms. So since, as I wrote in the abstract, I thought that you need to know more math in order to do better physics, I decided to, as I was thinking about it, to learn first the technique of playing the piano before giving great interpretations. So I went to the Courant Institute and I got a Ph.D. with Peter Lax. I did a lot of other things. One of them had to do with learning about data assimilation and meeting Jules Charney, who had written a paper with the people at Ghil about using the history of the temperature field, of the mass field, to derive the wind field. And so out of this came the first book that I co-edited with Leonard Benson and Erland Chauny. And the authors are in alphabetical order because I was in a math institute, but it was Erland who actually did most of the work. And then I did my PhD thesis on a nonlinear parabolic PDE, as it would have been called at the Courant Institute, and it was in the PhD, but which was really an energy balance model about which I learned from Steve Schneider and Sri Dalchen RP. So I was able to prove the existence of multiple equilibria, the nonlinear stability, and computed back-to-back saddle node bifurcations. And during this time, then I started doing more intensively data simulation. This is just a little figure illustrating the objects of sequential estimation, as the more general name is, and often referred to as Kalman filtering. As Norbert Wiener already put this in 1949 book, there are three problems: filtering, smoothing, and prediction. I don't have time to talk really about this. I'll just show you this bifurcation diagram for a nonlinear partial differential equation, which is written down, in this symbolic. These are partial derivative with respect to t, partial with respect to x. And basically, we have these three branches, which are connected by two saddle node bifurcations, one supercritical, the other one subcritical. And as a result of this sewing together the two, you get a hysteresis cycle, which was subsequently documented by trying to model snowball Earth, etc. And basically, what's so wonderful about bifurcation theory? Well, it tells you that while you are on a branch, you can pretty much linearize, but when you get to these things which generically are isolated, the bifurcation points, you have to pay more attention. So this also says something about climate sensitivity, which is just a tangent to this upper branch at the present moment. And it says something about the fact that we're quite close to falling off a cliff. Okay. So to continue, I then taught a graduate course with Steve Childress, who later also was the director of the Institute. And it resulted in the first book that was reissued by Springer just a few years ago, to use dynamical systems and their bifurcations as a basis of understanding nonlinearity and irregular behavior in the geosciences. Steve Childress, of course, wrote the part that had to do with the geomagnetic field. And then after hanging around for a little bit longer at UCLA, I moved at Courant, I moved to UCLA. And one of the things that I did there was with Fei Jin, who's now a full professor at Hawaii, but was in a postdoc plus mine and David's, and with David Nealon, used Floquet theory to deal with the seasonal forcing. So, here the forcing is not constant in time, and thus explain the paradox of irregular behavior in the presence of phase locking to boreal winter. This is what we call the devil's bleachers in this problem, which is a particular transition to chaos via, the devil's staircase, but if you look at it really in 2 dimensions, we call it the devil's bleachers. And then finally, I made it because of my wife, who's French, to the École Normale Supérieure, where with Michael Chekroun and Eric Simonet, we developed what will be essentially the end of the stuff. Okay, so climate change. It may be smooth or it may be rough. Tipping points, question mark. So this is one way of looking at the tipping point. This rock sits really on its tip somewhere in Australia, and you think that any moment it can. And if it doesn't, then that's, sorry, I need to have a watch here because it's going more slowly than I thought. So I will now put it to warn me in sufficient time that I'm getting a little bit behind. Okay, so another kind of tipping point is, of course, walking the plank, which was a standard punishment of the Pirates of the Caribbean. And then you have switching on the light and boiling water and rioting, revolution, in climate blocking, or falling asleep, which turns out to be pretty subtle. So the rest of the talk will have this little plan, and I'll see how much I can really cover. And if not, then you'll just have to invite me back next year. Okay, so intrinsic versus forced variability, short, intermediate, and long-term prediction, multiple scales of motion, the IPCC and its uncertainties, and then discussing greater detail, time-dependent forcing, pullback and random attractors and tipping points thereof. And with these illustrative examples, which I don't think that I might get through entirely, but at least I will try. And then conclusions, what do we and don't we know, and some beyond. Okay, so the first thing is that aside from the great contributions of John von Neumann to meteorology and numerical weather prediction, which pretty much everybody knows about, he was also an important player. He gave the introductory talk to a meeting in Princeton about climate, which only appeared several years after his untimely death and was edited by Richard Pfeffer. It was called Dynamics of Climate. So essentially what von Neumann said is, well, the initial value problem, that's the numerical weather prediction, that's easiest. The asymptotic problem, long-term climate, a little harder, you have to know a little bit of dynamic resistance, but it's the intermediate problem, which we call in climate sort of low frequency variability, that involves multiple equilibria, long periodic oscillations, intermittency, slow transients, tipping points, is the hardest. Basically, this is what they're trying to deal with. There are fantastic progress in this, and we know theoretically a little bit about this one, but it's this one which is really stuck in our throats. So in order to understand some of the difficulties, this is a composite spectrum of climate variability, which originally goes back to a review paper by Murray Mitchell in 1976, and this is my personal version from an article in the Encyclopedia of Global Environmental Change, but there are other versions thereof. Basically, what it says is that the climatic spectrum is largely continuous. This is, of course, just an artist image because we don't have a single time series that has resolution of seconds or minutes or whatever and lasts for the entire duration of the Earth. But so it's made up of little pieces, but overall it looks like this. Most of the variability is in the continuous spectrum. And then there are two well-known lines, you know, the rotation of the Earth around its axis and the revolution around the sun, or more precisely, the center of mass of this planetary system, which is very close to the center of the sun. And then everything else that is of interest are these broad peaks. And when Mary Mitchell wrote this paper, which was a year after I got my PhD at Courant, was no known source of deterministic internal variability. That was at least the opinion of a very large portion of the community at that time. Of course, my opinion was that, to be shown in subsequent papers, that these are simply broadened versions of Hopf bifurcations, you know, with various ways of broadening the peak. So now, why is this important for the overwhelming problem of climate change and its impacts on human life on this planet? Well, because we've been spewing up this much CO2 into the atmosphere, and if there were no nonlinearities and couplings, an exponential increase in CO2 concentration should lead to a linear increase in atmospheric temperatures. What we see instead is something much more complicated. So the question is why? Well, this also goes back to another encyclopedia. No, this is actually, sorry, the same encyclopedia article. But basically, it shows here a schematic version of the previous confrontation of these two lines. It shows something like the linear increase that you would have with just CO2 or other greenhouse gases do not follow this you know, exponential to linear behavior, but it is CO2 that is most important as confronted to this much more complicated stuff. So clearly, as opposed to the point of view of analyzing very complicated general circulation model runs, was done in the first couple of assessment reports of the IPCC, where even the first one chapters were sort of written according to expertise in particular feedbacks. So instead of having this scalar linear ODE, we need to consider a system of nonlinear PDEs that have poorly known parameters and multiplicative as well as additive forcing, and this is what we're trying to do. Okay, so this is again just to highlight the uncertainties that persist in spite of the enormous effort gone into these successive assessment reports. This goes now back to the fourth one, 2007. There's been a fifth one since then, and the sixth one is just coming up. But basically, the problem is the same. For various colors, which are the various scenarios of how smart or how idiotic we are going to be, there's still a huge uncertainty for each one of these lines. And this one decreased, it has rather increased since the China report 1979 to the National Research Council. So we need to, again, to do something about this. So the first thing that I think we need to do is to understand that the so-called equilibrium climate sensitivity as defined in the Charney et al. Report and summary thereof in the Bulletin of the American Meteorological Society is not really what happens. So you double CO2 in a scalar linear ODE, the temperature would be doing this and just settling into its new equilibrium. If instead, let's say the climate were purely periodic, say if ENSO were really periodic as opposed to being irregular, the temperatures would really be, the mean temperatures would be going up. There's no getting around that. Nobody has, I mean, some people have tried, but there's no good explanation for it going down. But at the same time, the period, amplitude, and phase of the limit cycle would be changing. Then what I call here is how some about real stuff, in other words, chaotic plus random. Again, the mean temperatures would be going up, but a lot of things, including the distribution of extreme events, would have to change. So how do we find out? Well, my poor opinion of this is that we have to take into account in a mathematically self-consistent way the time-dependent forcing. To just give you an idea of the confusion that arises if you do not do so, I mentioned ENSO here. Well, the linear southern oscillation, of course, occupies the oceanic component, occupies a large portion of the Pacific Ocean, tropical Pacific and beyond. That by itself is a large fraction of the Earth. So when you try to decide whether something has changed ENSO or whether ENSO has changed and therefore affected global temperatures, you do not exactly know what you're talking about. But you will if you learn about this stuff, which looks a little bit difficult, but we've tried to make it a little bit clearer than it used to be when it was just mathematicians talking to each other. Okay, so time-dependent forcing. So as I said, much of the theoretical work on the intrinsic variability of the climate system has been done with time-independent forcing coefficients. Okay, so this was, why did I say that it was good for about 50 years? Well, because in the early 60s, not just Ed Lorenz, but other people like, Hank Stommel actually before him and George Veronis at the same time had done essentially bifurcation exercises for the ocean with low order systems. And for numerical weather prediction, just the chaotic behavior of autonomous, or they're usually called differential dynamical systems, DDSs, was good enough to explain at least part of the exponential divergence of trajectories. So the address changes in time of the system's overall behavior and not just its mean properties. An important step is to examine time-dependent forcing and coefficients. The proper framework for doing so is the theory, as I said already twice or three times, non-autonomous and random dynamic systems. And here is a superatory introduction to pullback attractors. What are they? So again, if we take for a moment a linear scalar ODE, like the IPCC did in order to analyze its GCM outputs, so just x dot, time derivative of x minus equal to minus alpha x plus sigma t. Well, this is clearly the deterministic version. So if alpha is larger to 0, and if sigma were equal to 0, we all know what this does. It goes exponentially to 0. If sigma is not 0, in this simple case, you can compute analytically its pullback attractor, which is given by this and shown here. But in what sense can you define if there is time dependence in the equations, what the attractor is? It turns out that that is rather non-trivial, especially in the random case. It took Crowell and Flandoli a lot of work to really prove that there is what's now called a pullback attractor. So let me just show you here for a moment what is happening. What you would like to define is at a given time t, what the thing is attracted to. But you also have to take into account the time from which you start, which you denote by s. So I'll come back to this in a moment, but I will first show you the little video here, okay? So I say I am here, and I would like to know what is going to happen to all the solutions starting from some interval back here, more generally a compact set. So what you have to do is to pull back, okay? You have to pull back further and further until you see that everything converges because of the disintegrative nature of the system, the fact that alpha is larger to 0, to this point here and another one here, and so on. Okay, so let's then return to this. Okay, so the sources of non-autonomous dynamics, or of our mathematical understanding thereof, basically we are thinking about physically open versus closed systems. In other words, you have fluxes of mass, momentum, and energy between the system and its surroundings, okay, which is certainly the case of the climate system. Exchanges, radiation where the sun comes, incoming radiation, and outer space, outgoing radiation, and momentum with the moon, etc. So the mathematical framework of non-autonomous dynamical systems is appropriate for physically open ones. It starts essentially with the work of George Sell in the 60s on skew product flows. And the idea is that you have one equation in which the two things interact, but another one, that's the skewness of the system, which does not depend on X. Okay, so Q is called then the driving force for X. And the pullback work of, as I said, Powell and Thunderly and Ludwig Arnold, that they were the postdocs of at the time, or a snapshot as was defined independently by two physicists, Churchill, Gregosian, and Ott, with a postdoc of theirs, in which you have, again, in mathematical continuous time, what I wrote to you before. So now WT is boundary motion RD, and DT, the trick here, the reason we have to write two such things, for those who are not yet familiar, is that essentially DT, well, you can write it the opposite way, that dW is like the square root of DT, because going back to Einstein 1905, we know that the variance of boundary motion is proportional to time. So more generally, studying explicit time dependence in forcing, I have to move this off the screen. Enforcing or coefficients requires non-autonomous differential equation, the non-dynamical system. So just a little bit of Wiktionary. Non-autonomous is used both for the deterministic case and for a unified perspective on the deterministic and the random case. And the commonality between the two cases is the independence and the semi-group property of the driving force, which I will come back later. So whether it's Q, that's deterministic, or WT, which is stochastic. So likewise, pullback attractor is used both for the deterministic and random case, or in the latter case, one uses more specifically random attractor. Okay, so a random attractor, omega being the realization, is both invariant and pullback attracting. So if you don't digest these equations fast enough, just look at the picture. This yellow stuff is what was a straight line tilting up in the previous illustration. And these are pullbacks. These are these compact sets that from which you launch the flow. And these cross sections or snapshots, if you prefer, are what you are going to see at a given time. Okay, so moving right along, I see that I'm not doing too badly. Tipping points classification. So this is due to the work of Peter Ashwin and his colleagues in the Royal Society Philosophical Transactions. So there's bifurcation-induced tipping. I don't know how the due showed up here. So B tipping, there's a slow change in the parameter leads to a system passage to a classical bifurcation. So, bifurcations, as I said, have been around in the field at least since 1961, since the work of Hans Stommel on the thermohaline circulation. But nobody, people were confused by the Latinate polysyllabic word bifurcation. So now that you have tipping points and walking the plank and so on, this has caught the attention and we're talking a lot about it. Okay, then you have noise-induced tipping. So this was also known for a while. Random fluctuations lead to the system crossing an attractor basic boundary. And finally, the more interesting one, R tipping or rate-induced tipping, rapid changes lead to the systems losing track of the slow adiabatic change in its attractors. So all three types involve an open system, and we started with closed systems and studied their bifurcation structure, and then we proceed to the open ones and see how things change. So illustrative example, the Lorentz convection model with stochastic forcing, which we call LOHA, and its topological analysis, branched manifold analysis via homologies, and the grand unification of deterministic and stochastic points of view of climate dynamics. Okay, so I think that actually I can slow down a little bit and explain things. Obviously, if we were in the same room, I would encourage you to interrupt me, but it's a little bit difficult with over 100 participants and this Zooming stuff. So it turns out that under suitable mathematical circumstances, dynamical systems with time-dependent forcing or time-dependent coefficients have invariant measures, which are called in much of the literature disintegrated measures, because you have to integrate over them in order to get the classical Fokker-Planck point of view, okay? But which are called by Lyson Young, which I much prefer, as sample measures, okay? So we compute, we actually computed with Mikhail Shekun and Eric Simonet, the probability measure of the random attractor at some fixed time t, and for a fixed realization omega. So the point is that you're just looking at the sample path of the system. You do not look at the Fokker-Planck equation and the forward evolution of the entire probability measure. So we show a projection of, for a particular realization over y, so you see here the x and the z of the familiar Lorentz system, okay? And what we're looking at is the density of this sample measure. So when it's darker, there's more of it, and when it's bluer, it's thinner. And you see that this looks, well, at the carnival mask, but also a little bit like the Lorentz system with the origin, in other words, a state of rest, and the so-called conductive solution, and these being the convective solutions, which normally are just unstable fixed points. And so this is subject to multiplicative noise. So each one of the equations x1, y, z has this nonlinear deterministic part, which we know, plus this multiplicative noise. In this case, we have 10 million of initial points, okay? And here is what you see in greater detail. Sorry, it's not the same colors, and it's not the same ratio of the two coordinates. I mean, you know that the z coordinate is much longer than the x or y coordinates. But taking a lot more initial points will show you that the sample measure is indeed, as predicted by theory, supported on the so-called unstable manifold of the random attractor. You see that there's a very fine foliation. And furthermore, you see, you can still recognize a butterfly, you know, of the Lorentz strange attractor, but there are some holes in it, and there's other stuff happening, which I will now show you in a short video. Okay, so it's almost 2 minutes, but it's worth watching. So you see that the sample measure is advected by the deterministic flow field. There are some pretty ferocious animals popping up at some points. But there is a little jiggle of of each one of the streamlines, if you wish, okay, which is just the nature of the noise. But then there's a totally non-trivial interaction between the noise and the nonlinear deterministic flow. So in the interest of time, you can actually look this up you can look it up in the supplementary information of this paper, just if you click on this, you can see it in Physica D, but that's at a lower resolution. Or if you just click on this link, you are going to see it on the website of Mikhail Shekhun at UCLA. So I will now return to the story. Okay. So I told you that you see some holes. So we became interested in the topology of chaos. So people had already looked at the Lorentz 1963 stage attractor, but we're going to look at the random attractor. So the dynamics of a deterministic attractor can be compactly described as the limit of a semiflow on a branch manifold. The topological description, and this is algebraic topology. This is not point set topology, which more of you might know about. The topological description of the branch manifold encodes the invariant structure of the attracting phase space and describes a topological organization of the trajectory on the attractors. So here is just a cloud of points. So reconstructing a branch manifold from data, approximating a cloud of points in phase space by Euclidean closed sets, and then forming a cell complex out of these cells, and then identifying the branch manifold through the homology groups and torsions associated with a cell complex. We're not going to talk about the torsion. Torsions are what you do to a sheet of paper in order to get a Möbius strip, or to a very, very fluid bottle when you turn it, a regular bottle of wine, when whatever you like, when you turn it to a Klein bottle. But we're not going to talk about this here. We're only going to talk about the homology groups. So since I don't have a lot of time, I'll just tell you that H1 is a homology group that counts the number of holes. So this says that the homology group of the standard Lorentz attractor, fascinating as it is otherwise, is fairly boring. It's just Z2, there are 2 holes. Now let's see what happens to the random attractor. Okay, so here are just the same kinds of point clouds, but thinned out to be, as you've seen here, but at 3 successive instants in time. So clearly this random attractor changes, as I showed you that picture of the yellow stuff that was changing and where the snapshots could be quite different from each other. So these are the point clouds 0.07 in non-dimensional time units apart. Okay, so this is one, and this is another one, and this is a third one. Okay, so the homology groups that correspond to these are Z3. There are 3 holes, this one big hole and these 2 small holes. Then just a very small time thereafter, there are 10 holes. And I have a reserve slide somewhere to show you. You can see that aside from these 2, and there are 2 more here, and there's some other here. And then you are back to 4 holes, and here it's sort of hard to see because of the projection. So clearly, this fact that the noise has a topological effect on the nonlinearity is clearly confirmed by this analysis. Okay. There are rapid transitions, which we tentatively call topological tipping points, that change entirely the structure of the attractor, as you could have noticed visually from the video. Okay, so now I still have a few minutes for the grand unification. This is a classical strange attractor. Boy, you know this one. So physically closed system modeled mathematically as autonomous. There's neither deterministic nor random forcing. You can think of the deterministic one as being anthropogenic, but I'm not so sure. And what I refer to random is things like volcanic eruptions, or for that matter, what happens within a cloud on much smaller scales than the ones that you can resolve. So in this case of the autonomous Lorentz system, the attractor is strange, but still fixed in time. So, human beings don't like things that they're not used to. So, numbers started by being natural, and then they became rational, and well, they became integer, and then rational, and then irrational. So same way attractors, which started out as fixed points, and then as limit cycles became strange. Climate sensitivity is a change in the average value, the first moment of the coordinates x, y, z as the parameter lambda changes. In this case, there's exponential divergence according to the general theory, the classical view of dynamic system theory, that the positively upper-norm exponent, which Lorentz 63 certainly has, trajectories diverge exponentially, but the presence of multiple regimes in this system and in nature implies a much more structured behavior in phase space. Okay, so this is out of an article by Lenny Smith in the Encyclopedia of Atmospheric Sciences. You start with a PDF peaked at the origin, and then you follow this trajectory. And this is exactly what John von Neumann was saying, that the intermediate time is the hardest, because eventually you still wind up with a broad peak at x and y equal to 0, okay? But in between, you have all this crossing of motion between two regimes, okay? So this is the deterministic point of view. The random attractor now is a physically open system, modeled mathematically as non-autonomous, allowed, as I said, for deterministic and random forcing. And the attractor is pullback, in other words, even worse than strange, as it evolves in time. So it's like an imaginary or complex number. Climate sensitivity is a change in the statistical properties first and higher order moments of the attractor as one or more parameters change. So these are just cross sections or snapshots of the video that you've seen before. Okay, so this just shows you, even without the homology groups, that the number of holes changes. So, the grant comes from some PR person of the European Geosciences Union. When I got this Wegener medal, which is sort of the highest medal of the whole thing, told me that you have to give this some pompous name in order to attract attention. Okay, so the pompous name was grand unification. I didn't come up with this. Okay, so the deterministic, nonlinear deterministic point of view, line 63, climate is deterministic and autonomous, but highly nonlinear. Trajectories diverge exponentially. Forward asymptotic PDF is multimodal on intermediate times. Hasselmann, Tellus, 1976, same year as Mary Mitchell, climate. Okay, I'm almost done. Climate is stochastic and noise driven, but quite linear. Trajectories decay back to the mean. Forward asymptotic PDF is unimodal. So it's this picture, okay? And the grand unification that climate is deterministic plus stochastic, as well as highly nonlinear. Internal variability and forcing interact strongly. Change in sensitivity refer to both mean and higher moments. Okay, conclusions and references. So what do we know? There are great uncertainties in climate sensitivity and prediction. Some are irreducible. The climate system is open and affected by time-dependent forcing, both deterministic and stochastic. There's a nice general framework for including time-dependent forcing, NDSs and RDSs. What do we know less well? How does a climate system really work? Well, I apologize to various academies that have written on their websites that the problem is solved. Now all we have to do is take action. There is certainly enough knowledge to take action, but we don't really know what the climate system works. There are still discussions about whether the ocean is thermally or wind-driven, and whether the distinction makes sense. Whether certain things, some of those hot bifurcations leading to some of those broad peaks are intrinsic to one component or due to interaction between components, etc. There's smooth and rough dependence on parameters, tipping points, crisis. Again, I haven't had the time to cover that really. And how do the latter affect the intrinsic variability, namely higher moments, in particular distribution of extreme events? What to do? Well, work the model hierarchy, in other words, simple as well as highly, very detailed model, and of course, the observations. Don't get lost in your screen and in your big computer. You know, there's some atmosphere and ocean out there, and explore further non-autonomous and randomly driven models and their tipping points. And here are some general references where I'm attracting particular attention to the ones highlighted. And actually, these are some of the people that I would suggest that you ask to follow up. Peter Ashwin, Mikhail Shekroun, Valerio Lucarini, and eventually, sorry, I didn't highlight this, Denise Shamayla. So thank you very much. That's all for today, folks. I will stop sharing and be back with you.